Hello everyone, welcome to my talk, No IP, No Problem, Exfiltrating Data Behind IAP. So thank you for joining today and preferred hearing about GCP security other than eating lunch. And this talk going to be focused on one service in GCP. The service is Identity Aware Proxy. We'll explain what this service is, how it works, and how attackers can abuse it to exfiltrate secrets. So my name is Ariel Kalman. I'm a security researcher at Mitiga, and I came all the way from Tel Aviv, Israel. And a fun fact about me, because I had to put something, is that I prefer dogs over humans. So the agenda for today. I'll start by explaining what is Identity Aware Proxy and how it works behind the scenes. I'll show to you two IAP misconfigurations that we saw in the wild too many times. I'll do a quick introduction to what is cross-origin resource sharing and how is it related to IAP. And the last part will be an IAP configuration that, if enabled, allow attackers to exfiltrate secrets from sensitive environments. So what is Identity Aware Proxy? It's basically a service in GCP that acts like an identity firewall. It sits in front of your application and intercepts any request to that application. It controls the access to the app based on identity, and by default, it blocks any unauthenticated request to the application. And it also has some interesting settings that I will dive into later. So how IAP actually works. When the user tries to access an application, he sends a request to the application, and the request hits the endpoint of the app. Because we used IAP to protect that endpoint, the request is forwarded to Identity Aware Proxy. He will check if the request is authenticated or not. And if the request is not authenticated, he will redirect the user to a Google sign-in page where he needs to put his email and passwords to log into his account. If the user was successfully logged in to his account, he then needs to be authorized to make sure he has sufficient roles to access the app. Then, if the user both authenticated and authorized, IAP injects the authentication headers to the request and forwards it back to the application. From that moment, the user can interact with the application without feel IAP in the middle each time. So, now that we understood what is Identity Aware Proxy and how it works, let's see two IAP misconfigurations. The first misconfiguration is overly broad IAM grants. When you use IAP to protect an application, you need to explicitly specify which users can access the app. And in GCP, we have two spatial member types. The first type is all users, meaning every user in the world, no matter if it's authenticated or not, like an anonymous user. And the second type is all authenticated users, meaning every authenticated user to a Google account, no matter if that account is part of the organization or not. So adding one of them to the list of users that can access the app effectively disabled IAP, because now when the user gets to the authentication and authorization part, he can just go through. This is how it looks in the platform when you do this kind of misconfiguration. You can see a screenshot from the Cloud Console, and you can see me adding all users member type to the list of users that can access the application. When I do that action, I get a warning saying, adding all users makes this resource public and accessible to anyone on the internet. So that's a great thing. However, when I do the exact same operation via the G-Cloud CLI, I get no warning, and the operation just executed quickly. And it emphasizes how easy it is to make such mistakes that effectively disabled IAP, even though you used it. The second misconfiguration is exposing a bypass path around IAP. So as many of you know, many applications have multiple endpoints. And when you use IAP to protect an application, you need to explicitly specify which endpoint is protected by IAP. Like you need to configure it for each endpoint. It's not like you can protect using IAP the entire application. You need to choose endpoint and enable it for it. So if for some reason an admin mistakenly forget one endpoint, attackers can sneak in through that endpoint and access the same data of the application. This is just a diagram to show how it looks. You can see an attacker tries to access the application, but he is unauthenticated, so he cannot access it. However, the application has another endpoint, the purple one, which is not protected by IAP, meaning that the attacker can send the same request to that endpoint and access the same data of the same application, even though it's kind of protected by IAP. So it also highlights how easy it is to forget one endpoint and effectively not using IAP to protect the application. So I showed to you two IAP misconfigurations, and now let's do a deep dive into one risky setting that, if enabled on IAP, allow attackers to potentially exfiltrate secrets. So the name of the setting is Allow HTTP Options. And the description says, control HTTP options, coarse preflight. But to truly understand that setting, we need to first of all understand what is coarse and what is coarse preflight. So when you search online what is cross-origin resource sharing, or coarse, the first result that you see saying it's something that's designed to annoy developers. It works by giving you errors, leaving you scratching your head. While it's sometimes true, let's demystify it a bit and explain how it really works behind the scenes. So what usually happens when a user accesses a web page is that it sends a request to the application and gets back the response, HTML, JavaScript, CSS, and images. And sometimes, some of these resources are hosted on a different server on the internet. So to fetch these resources, JavaScript has a built-in function called fetch that fetches resources from a different server. It basically sends another request, cross-origin one, to that server asking for that resource. But now, let's see what happens if instead of that legit JavaScript code, you get a malicious JavaScript code that tries to send a GET request to the bank server account, to the bank account server, and asking for sensitive information. You want to block this kind of attack. And this is why most browsers today have a built-in security feature called Same Origin Policy that basically prevents websites accessing other websites' data without their permission. So what happened here is that the bank server will get the request, check if he wants to allow it access the data or not, and then he will respond with a special header called access control allow origin. And this header will be an integral part of the attack that I will show later, so keep it in mind. So the bank server put the value of the origin that made the request if he wants it to allow access the data, and if not, he will put an empty value in this response header. He sends back the response, and my browser will check if the origin that made the request is equal to the value in that header in the response. If they are equal, it means that the bank server allows us to access the data. And if not, my browser drops the response and not allow me to access the data. So it's cool. This is how this kind of attacks can be prevented by this Same Origin Policy security feature in web browsers. But now let's take it one step further. Imagine that instead of that malicious JavaScript, you get a different JavaScript code, which is also malicious, that sends a post request instead of GET request to the same bank server, trying to do money transfer operation from account A to account B. Because the bank server will get the request and execute the money transfer operation before my browser will get back the response, my browser cannot prevent this attack using the same method that we showed earlier. So this is why Same Origin Policy has another layer of security called coarse preflight. And coarse preflight is a special type of HTTP options request that is sent by the browser before the real request. We basically ask the server, is this request allowed? Like the original request that I wanted to send, the post request, is this allowed or not? If the bank server says yes, my browser sends the real request, and if not, he drops it. So this is how the second attack can be prevented using coarse preflight request, like a conversation between the browser and the server asking if this request is allowed or not. And one key note to know about this HTTP options request is that they are unauthenticated. And this is by design. It's supposed to be lightweight and simple process of communication between the browser and the server. And it cannot be changed. So we understood what is coarse and what is coarse preflight. Let's get back to the setting that I showed earlier. The name of the setting again is Allow HTTP Options. So I said in the beginning that IAP by default blocks any unauthenticated request to the application when you use it. However, HTTP options requests as part of this preflight process are unauthenticated. So it means that by default, IAP blocks any HTTP options request to your application. And because this process of communication between the browser and the application is mandatory for applications to work, it basically prevents apps behind IAP from working with cores. And this is why GCP added a setting to IAP that can be either enabled or disabled. If enabled, it allows HTTP options requests to go through IAP without authentication. And if not, it drops it. So this is before we enabled the setting. The user tries to send HTTP options request to the application, but the request is unauthenticated, so IAP blocks the request. And after we enabled the same setting, allow HTTP options, the user can send the exact same request, bypass IAP, and reach the application without a token. And after we enable the setting, it means that only HTTP options request can go through IAP. Any other request, like a GET request, POST request, or any other type, is still blocked by the IAP if it's unauthenticated. So here I want you to focus on the header, access control allow region. This is the same header that I showed earlier, and this is the header which the application specify which domains can access this resource using cross-origin requests. But let's think what happens if the attacker can control the response. What happens if the attacker wants to use this kind of header in order to exfiltrate secrets? That will be the exact attack that I'm about to show. So before I explaining the attack step by step, I want to explain the prerequisites, because we have a few, and the diagram. So the first prerequisite is that we have an application, in this case App Engine in GCP, and we have IAP, which is protected, which protect that application. And we have the setting allow HTTP options enabled on this IAP. This is the first prerequisite. The second prerequisite is that we have some kind of initial foothold inside the environment. The attacker must be able to execute operations, execute code. It can be a VM, it can be a Cloud Run, it can be any form of code execution inside the environment. And we have also the external attacker, which is just a VM on the internet. And the internal attacker has an identity with the role App Engine Deployer, which is a very commonly given role that's been given to developers that needs to deploy their new versions to the applications. So our goal is to exfiltrate a secret from the internal attacker to the external attacker. But this environment is very sensitive and restricted, so the internal attacker cannot just send a request to the external attacker or any data directly, because we have a firewall that blocks any outbound access from the environment to the external attacker. Also, the external attacker cannot access any resource in the inside environment, because all resources are accessible only via private access, and IAP protects the application, meaning that the external attacker must have a token, which he doesn't have, in order to access the application. So again, we want to send data out. The first step of the attack, out of 3, is that the internal attacker deploys a new version to the application. It's just a YAML file with multiple configurations, where the internal attacker, it looks like this, and the internal attacker puts the secret that he wants to exfiltrate inside that setting, access control allow origin, that originally intended to define to the application what to respond to HTTP options request. But in this case, we abuse it to put a secret inside that header. It can be any kind of secret, anything that can be encoded into characters can be put inside that header. So the internal attacker deploys this version of the application to the App Engine. The second step is that the external attacker sent an HTTP options request to the application. Because we allow HTTP options on the application, the request can go through without a token. This is how it looks. And the third step is that the application responds with the secret. This is how the response looks like. And you can see the header that we talked about a few times, the access control allow origin, that contain my secret. In this case, it's a shrug, but it can be anything. So this process, these 3 steps, can be automated to happen over and over. The internal attacker deploys a new version with a new secret, and then the external attacker fetch it from the outside. And then the internal attacker deploys a new version with a new secret, and the external attacker fetch it from the outside. And I was able to automate this process just out of curiosity to see how much data I can exfiltrate using this channel. And I was able to exfiltrate 15 megabytes of data in 1 day. And I know it doesn't sound like much, but it's enough for the internal attacker to exfiltrate secrets, tokens, and certificates that can be later be used by the external attacker to expand the attack surface on the environment and access more resources. That's it. Now let's see how it looks in the logs. Here you can see a screenshot from the GCP logs. And on the left, you can see a spike in the number of operations that happened during that time window. And on the right, you can see that the same event happened over and over. Create version on App Engine happened every 30 seconds. And this is logged on the first step of the attack, where the internal attacker deploys a new version to the application. One row is logged. And inside that log, you cannot see the actual YAML file that the internal attacker deployed. So you cannot see if it's a really malicious one or not. But this is a very weird activity. Like, no developer needs to deploy his new version to the application every 30 seconds. And this is why it's so easy to detect. This is an example of a detection for this kind of attack. It combines of 3 steps. The first step is filter the relevant event. In this case, create a version on App Engine. The second step is to group by the events and count the number of times each event, count the number of times the event happened for that user during that time window. And the third step is to filter the number of times, the amount of logs that you want that are suits for your environment. So that's all. This is the only detection you need to detect this kind of attack. And also, this is the only detection you can write for this kind of attack, because the only part that is logged inside this whole 3 steps process is the first step, where the internal attacker deploys a new version. The other 2 steps are not logged in cloud-native logs. That's it. Let's do a quick recap. So I showed you what is identity-aware proxy and how it works, and also what is cross-origin resource sharing and how they are both related somehow. I showed you 2 IAP misconfigurations that are relevant to different services also, not only to IAP. And I showed you how you can abuse IAP setting to exfiltrate secrets from sensitive environments. And the last part was how it looks in the logs and how you can detect it in your environment. Thank you for listening, and I'm open to take any questions outside later if you want. Thank you.